Oh, did I save the best for last? So everyone, let's put things together. If we squint our eyes and not look very closely at the integrand's position, kind of looks like I have a sum of two squares. Looks to me like eventually I'll have some kind of tangent substitution. However, notice how this numerator is a degree larger than the degree of my denominator. Now you can perform Pauling long division to rewrite this improper rational expression as a sum of some polynomial with a proper rational expression. Go for it. I'm tired, I'm lazy, I tend not to go through all that work. So I'll just add a funky looking form of 0. That's my approach. When I teach my 9th grade algebra students Pauling long division, I show them this alternative of adding a funky form of 0. That's my numerator. But wouldn't it be nice to have this numerator? Because if I add these two extra terms, doesn't this fraction right here cancel just an x? It's nice. But of course, I've committed a lie. Technically speaking, I didn't have these two terms upstairs, so let me compensate by subtracting them out. I just added a funky looking form of 0. Now, that being the case, notice how this term right here is that term with sign change. And so let's try to make this term that term with a sign change. So here I go. I lied again. That should have been a negative 2x. I'm missing a term with a negative x. I'll put it in. I'm still lying. I added a negative 2 to that numerator. I'll compensate by adding a 2. At least this fraction right here collapses quite nicely. Now take a peek at what's left over. There's negative x plus 2. It sure would be nice if that 2 weren't there. It sure would be nice if 2 was a negative 1/2. After all, take a peek at how if you differentiate this, you get a 2x plus 1. Notice a constant is half the coefficient of the x. So I'll make sure this 2 is half the coefficient of that x. I'll rewrite the 2 as a negative 1/2 plus 5/2. I know I'm walking a little fast right now, but once you see what I'm doing, it'll be an absolute piece of cake. Take a peek at the denominator, which is that trinomial. If I commit to completing the square, don't I get this? I don't know. In this way, I just think I can be lazy. I can just state the answer. So why don't you and I dive in and do just that? Oh, look how far we've come. We're getting quite sophisticated. So let's see, term by term, anti-differentiate. Is that going to be this? Now, can you imagine multiplying top by negative 2? If you do, that's the truth of this. I'll compensate by pulling out a negative 1/2. Now, commit to u sub. U being everything downstairs, the numerator is its derivative. And so that's just going to give us a natural log. Now, as far as my last term is concerned, if it makes it easier for you, you could let z be equal to this binomial that's being squared. But if you do, notice what's left over. Something like a 1 over x squared plus a squared. But you already know about that. To anti-differentiate this, here's what you get. Now, you have seen that in first semester calculus. To anti-differentiate this, you get this. I hope you saw that in first semester calculus, but if you haven't, don't worry about it. Take this and differentiate it. You'll see you get what's in the integrand's position. Or make a substitution. You definitely did see this in first semester calculus. I hope you saw this, but if you didn't, again, take this, differentiate it. You'll get what's in the integrand's position, or go in the forward direction by committing to a substitution. So even though this and this might be new to you, tiny, tiny extension from what you had in the past. So if you're okay with this, I'm going to exploit it. This is what I'm going to use next. So anti-differentiate this term. This gets pulled out. I get my 1 over a. Inverse tangent of this over the square root of 7 over 2, but the 2's upstairs and downstairs will cancel. And I'll clean up here. Oh, that wasn't bad. Actually, that was an absolute piece of cake. We didn't even have to do a trig substitution.